Hello and welcome to another video on the topic of eco-modernism. Today we're looking at transport, how the many ways we get around are contributing to the upcoming climate catastrophe, and what we can do about it. Of course, this is something close to all our hearts, because we all have to get around. Some places are more pedestrian friendly than others, but you can't walk or cycle for all of your journeys. And even if it's not you doing the travelling, the things that you buy, the food, the clothes, the medicines, are all transported from the places where they're made to the places they're sold and eventually to you. And the people who work in these factories and shops all have to get around too. So transport is not something we can avoid. We all rely on it, and we have to think carefully about how we might be able to reduce its impact on our world. To start off, let's look at the impact itself. For hundreds of thousands of years, human beings moved under their own power, or under the power of various beasts of burden, from horses to oxen to camels and so on. Strictly speaking, animals weren't entirely carbon neutral, depending on what they're eating, but they're close enough. We also invented wind power to get us across the seas and oceans of the world in the first boats. The wind is entirely carbon neutral, of course, though the processes used to make the boats themselves often weren't, and the countless inevitable shipwrecks littered the ocean floor with the debris that today's archaeologists now study. Also, to build a large galleon took hundreds of trees. A large ocean-going warship would take a couple of thousand oak trees or more, and these ships were being built at an enormous rate. By the mid-16th century, the Tudor navy consisted of nearly 100 ships of that size. If you get 20 to 30 oak trees per acre, then we're talking about maybe 80 acres per warship, or 8,000 acres for the entire fleet. And that's just the ships, not including the dock apparatus required to construct them, the carts to transport the raw materials, and the homes in which the dock workers lived. So even when we made our transport vessels out of wood, it still had a significant environmental impact. But it was the invention of steam power that really started the ball rolling with the environmental damage. Steam power, at least in the 18th and 19th centuries, meant burning wood, or more likely coal, to generate heat. The heat boiled a tank of water, the steam from which expanded, and that expansion created the power required to turn wheels. But, as we now know, the burning of coal, though it was a cheap and energy-dense fuel, is destructive to our environment for many reasons. Not only does it release a significant amount of particulate pollution, causing over 1 million premature deaths worldwide every year, but it's also a major contributor to climate change. The internal combustion engine, which came along in the late 19th century, was really just another step in the wrong direction. Again, refined oil does contain a huge amount of energy and is fairly easy to store and transport, but it is also highly flammable, which is why it's such a good fuel, but also why it's so dangerous. And again, it's a huge contributor to the accumulation of greenhouse gases. This image tells you the story as of today. These figures are for the UK, but it's a similar picture across the developed world. 120 million tonnes of CO2 emissions per year come from transport, the second largest source just behind electricity and heat. And if you include aviation and shipping too, and I'm not sure why they're separate here, then transport is indeed by far the largest contributor, at over 160 million tonnes per year. These are figures from 2016, a year when the UK's total CO2 emissions were almost exactly 400 million tonnes, so transport is 2/5 of that, or 40%. These figures from Our World in Data show the statistics for 2018 globally. As you can see, road transport creates the bulk of emissions, with aviation and shipping at roughly 10% each. Transport globally produces roughly 1/4 of all CO2 emissions. Well, we've seen the impact of transport and it is enormous, but what are the individual sources and which solutions can we offer in each case? Does the same solution work for all cases, or do we need to tailor the solution to the use? This 2018 study by the European Federation for Transport and Environment investigates the impact of private car travel on the environment. In the EU, 72% of the emissions from surface transport, that is, excluding boats and planes, came from cars and vans, with the bulk of those, roughly 500 million tonnes CO2 equivalent, from cars. From the official figures, it looks like the emissions of those vehicles have been dropping for the last decade, but in reality that's because the tests from which those numbers are calculated have become further and further away from reality, with the car makers building cars that perform well on the specific emissions tests but poorly in real-world conditions. It's very clear that internal combustion engine vehicles, for most uses and especially for private use, are not going to play a part in our future over the next couple of decades, with countries such as the UK promising to phase out purchase of new fossil fuel burning cars by 2030, and Norway promising the same by 2025. The days of the internal combustion engine are indeed numbered. We can't keep burning stuff to move us from A to B. But what are the alternatives? The primary alternative seems to be battery electric. At least by the most recent industry figures, there were something like 7 million battery electric cars on the road at the end of 2019, according to these figures from the International Energy Agency. And that number is increasing at an exponential rate. In the UK, according to the official government vehicle licensing figures, these are the top makes and models of ultra-low emission vehicles registered in the UK in 2019. As you can see, they're all battery electric, or plug-in hybrids. Hybrids will also be phased out by the 2030s. As you can see, battery electric vehicles are the only show in town. There are some who think that hydrogen cars are a good idea, and their biggest positives are a longer range, much faster refuelling time, and a reduction in the expensive rare earth metals required to manufacture them. But currently we have no way of generating green hydrogen in the quantities required. Hydrogen itself is enormously dangerous and explosive, and we would need to build out a filling and refuelling network rather like what we currently have to refuel petrol and diesel. With electric vehicles you only need an electricity network, and we already have one of them. Besides, the longer range is irrelevant for the overwhelming majority of journeys, and fast refuelling is only relevant because it's very difficult to get a hydrogen pump installed at home. You only need to fast charge a battery electric vehicle if you're going a long distance, and the overwhelming number of car journeys are significantly shorter than the range of the average battery electric vehicle. The primary arguments against battery electric cars are the resources required to make them, the whole lifetime CO2 cost, and specific issues like range anxiety, charging infrastructure, and upfront cost. Let's take those one by one. Firstly, the resources required, which is an absolutely valid criticism. However, though batteries do require a lot of resources, they are almost 100% recyclable, so when they come to the end of their lives you can extract the raw materials and reform them into a new battery. The reason batteries degrade isn't that the resources are spent in some way, but merely that they lose their initial configuration. You can't say the same for petrol. Once it's used, it's gone forever. The upfront cost is indeed higher than petrol cars, though the cost is also coming down, and in a year or two it should be roughly the same. However, the lifetime cost is much less for a battery electric car, as they're so much cheaper to run. UK insurance firm Direct Line estimates that the lifetime cost for a battery electric vehicle are roughly £1,500 less than for an equivalent combustion engine car. And of course the price of battery electric vehicles is coming down rapidly, so the lifetime savings are getting larger every year. This leaves a couple of genuine issues, like complaints about the inadequate charging infrastructure in most countries. If you don't have the ability to have a charger at home, it's not easy to charge an electric car, and hence range anxiety is often a worry for people, especially if they think about the 1 or 2 long journeys they make each year, not the hundreds of shorter ones. Finally, we need to address the incorrect accusation often made that battery electric vehicles are worse for the environment than a combustion engine car, because the electricity is generated by burning fossil fuels in many cases. Personally, I recharge my car from my solar panels as much as possible. But even if you were to plug your car into the average electricity grid, and even in the dirtiest grid in Europe, which is Poland at the moment, the lifetime CO2 emissions for that car would still be significantly lower than for an equivalent internal combustion engine car. And of course, those emissions are coming down considerably as our grids decarbonise. One way to improve the efficiency of our transport system is by relying on economies of scale. A bus can carry dozens of people, but creates far fewer CO2 emissions than the equivalent number of cars required to carry that many passengers. If everyone used public transport instead of private cars, then the amount of CO2 emitted by our transport network would drop considerably. Using numbers from this paper by the UK government, a medium-sized car emits roughly 130 grams of CO2 per passenger per kilometre. A bus emits only roughly 70 grams CO2 per passenger per kilometre, just over half the amount. A train is very similar at roughly 65 grams CO2 per passenger per kilometre, though an electric train would be even less and is getting lower every year as our grid decarbonises. So moving to public transport could significantly reduce our CO2 emissions, but looking at the numbers, it can't possibly have enough of an impact to make the problem go away. The best we could imagine would be for every single car passenger to take public transport instead. That would save roughly half of the CO2 from those cars, but some transport miles are already taken by public transport, especially around large cities, so this wouldn't reduce the total amount of CO2 emitted by transport by half. Also, many journeys just can't be completed by public transport, especially for people with large loads to carry, or doorstop deliveries, or transport for those who are extremely frail or severely physically disabled, or just for those who live in the country nowhere near a major public transport interchange. One last point is that all road-based transport will be much more efficient if there were fewer vehicles around causing traffic, and therefore not only forcing vehicles to spend a lot of time stationary, but also slowly edging forward with the engines running the whole time, pushing a lot of pollutants in the air at specific locations. So if people moved from cars to buses, or just from one passenger per car to ride-sharing, that would not only reduce the CO2 per mile because you're moving from an inefficient vehicle to a more efficient one, but also you would be making all of the remaining vehicles on the road slightly more efficient by reducing the traffic, and therefore reducing pollution overall. Sea transport is usually considered separately from land transport because the environmental impacts are of a different type to those caused by road and rail travel. However, the CO2 emissions are just as real, and sea transport is responsible for roughly 2.5% of all CO2 emissions globally. It seems like a clean thing to do, especially as ocean transport was the original method for moving large loads long distances thousands of years before the internal combustion engine was even invented, and historically it was a zero-carbon process. But in the 21st century, ocean-going vessels have got very large indeed, and large vessels take a huge amount of fuel. These statistics come from the FreightWaves site and state that the very largest of container ships can carry as much as 4.5 million gallons or 20 million litres of fuel, which is 16,000 cubic metres. Ships going through the Panama Canal carry up to 3.5 million gallons, and at a standard speed they consume 63,000 gallons of fuel per day. That's nearly 300,000 litres per day, or 3 to 4 litres per second. CO2 emissions for fuel oil are roughly 3.1 kilograms CO2 per kilo of fuel, according to this study by the International Maritime Organization. This means that a large container ship is generating roughly a ton of CO2 per minute. The International Maritime Organization also calculates that the impact from all shipping globally is roughly 1 billion tons of CO2 equivalent, comprising slightly over 2% of all greenhouse gas emissions globally. That's roughly the same as all of aviation. Shipping seems clean because it's out of sight, and we don't hear boats roaring past as we do hear and see aircraft overhead, but shipping is still a significant polluter. How could we clean up the shipping industry? Well, it seems unlikely, at least for now, that we could replace all that fuel with batteries. Let's do a quick back-of-the-envelope calculation. The battery in a Tesla Model S P100D car is 100 kilowatt hours, and it weighs 625 kilos. Its efficiency is 22 kilowatt hours per 100 kilometers, which means if you combine those numbers that it takes roughly 138 kilograms of battery to go 100 kilometers. Let's compare that to the Mercedes-Benz S-Class, which is a similar price and weight but has an internal combustion engine. The Mercedes does an average of 35 miles per gallon, which means roughly 8.1 litres per 100 kilometers. 8.1 litres of petrol weighs roughly 6 kilos, so to go 100 kilometers you need either 6 kilos of petrol or 138 kilos of battery, which is 23 times as much mass. You can see the problem. When we scale this up to a giant container ship, the amount of batteries required is going to be vast. This was only a very rough calculation, but the conversion factor of approximately 2 orders of magnitude, or 100 times, holds between batteries and fossil fuels when you look at slightly more detailed estimates. That's okay for cars, where the mass of fuel wasn't too significant in the first place, but for a transport ship with 20 million litres of fuel, you're talking somewhere in the region of over 1 million tonnes of batteries to run its 64 megawatt engine. For a ship of that size, the maximum carrying capacity is roughly 180,000 tonnes, so carrying more than 5 times its maximum capacity in batteries seems implausible. There is an alternative though, hydrogen. Hydrogen is actually extremely energy dense, nearly 3 times as much as fuel oil, which means you could easily fuel up even the largest container ships in the world with hydrogen, if you could convert its engines to support that. The problem with hydrogen at the moment is that it's mostly made from fossil fuels, but that is changing. Green hydrogen produced entirely from green electricity being used to electrolyse water is definitely growing, though it's still a tiny fraction of the total. Global demand for hydrogen has risen 50% in the last decade and currently stands at roughly 75 million tonnes per year. This facility in Fukushima, Japan, produces 1,200 cubic metres of green hydrogen per hour using a 20 megawatt solar array. That's a lot, but I reckon it would still take 2 days of continuous sunlight to fuel up the largest container ships, and it's likely to be considerably more expensive than fuel oil for the foreseeable future. Oh, and hydrogen is insanely explosive, so you're basically sailing an enormous floating bomb. Still, it's a start, and frankly, unless we see a staggering improvement in battery energy density, then it's the only option. Well, I guess there is one other option. The other fuel that is way more energy dense than even hydrogen is uranium. Lots of military ships are already fueled by fission reactors. The technology is very well known, and it emits zero CO2. The USS Nimitz-class aircraft carriers have 2 nuclear reactors on board. They can operate for 20 years without any refuelling. They take up relatively little space compared to liquid fuel, and they have a service life of over 50 years. If we made them in bulk, then the costs would drop considerably. And it has actually been tried a few times already, though without mass adoption the economics don't really work. Still, I think it's arguably the best option we have. Air transport is another segment all to itself because it has its own challenges and limitations, though it is also responsible for 2% of all greenhouse gas emissions worldwide. Air travel is by far the fastest way to travel between any 2 distant points for most of us, and it is vital for our advanced economies. But pushing 1/3 kilograms of aircraft into the sky with hundreds of passengers plus all the luggage and fuel takes a huge amount of energy. And currently we're sort of stuck here because of a simple consequence of basic physics. As you saw with my analysis of electrifying shipping, batteries are very heavy, so in order to put enough of them on an aircraft to power it for an entire flight, you would basically need to ground the aircraft permanently, literally a non-starter. There are a few options though. Firstly, if you're only travelling short distances, then you can indeed run a battery-operated passenger drone. The technology is well known, they don't have to climb very high and they run for tens of minutes instead of 15 hours. The maximum range would be 10 to 20 kilometres, and they'd carry 2 passengers rather than 200. But there is definitely a niche here, especially for those who live on isolated islands, or commuting to and fro from distant or inaccessible locations such as offshore industrial facilities. And, of course, the mega-rich hopping between skyscrapers. But for the rest of us, electric air transport is little more than a myth. It's extremely unlikely ever to happen unless we can get at least an order of magnitude improvement in energy density, probably 2 orders of magnitude. And the trick to switch to nuclear energy doesn't really work here either, because even smaller nuclear power plants are generally too large and weighty for an aircraft. So we're really only left with hydrogen again. The aircraft manufacturer Airbus has recently publicised its own internal push towards hydrogen as a part replacement for aviation fuel. The concept aircraft 0E could enter service by 2035 and would run entirely on hydrogen. Airbus predicts it will be able to transport up to 200 passengers, 2,000 nautical miles or 3,700 kilometres. That couldn't quite get us across the Atlantic, except maybe with a stop off in Iceland on the way. But it could get from London to Cairo, or maybe just about from New York to San Francisco if you're lucky. Last but not least, something that we often miss out on lists of transport is space travel. We miss it out because, of course, up to now it's been almost entirely negligible compared to the billions of cars on the roads globally and the hundreds of millions of kilometres flown by aircraft every day. To work out the environmental impact of spaceflight, I turned to the always excellent Tim Dodd, the everyday astronaut, who made the following calculations on his webpage, the link to which is in the description below. Looking at the main fuels or propellants for rockets, there are a few very popular ones. Hydrolox, which is a mixture of liquid hydrogen and liquid oxygen, powered the main body of the space shuttle, and it burns very cleanly with no greenhouse gas emissions. However, the solid boosters, seen here on the sides of the shuttle, are significantly less clean. One shuttle launch emits roughly 440 tonnes of CO2, in addition to lots of water vapour and ozone-depleting gases. Building the average home will emit roughly 80 tonnes of CO2, so a shuttle launch is roughly 5 houses. It does also deposit a large quantity of particulate matter in the atmosphere, soot and nitrogen compounds, which can also contribute to global warming, not to mention causing ozone depletion and worsening air quality. What about more modern rockets? Well, many of them burn fuel called RP1, which is a bit like an enhanced aviation fuel. It's not very pleasant stuff, but not massively more polluting than ordinary gasoline. A SpaceX Falcon 9 rocket burns roughly 500 tonnes of the stuff per launch. An Airbus A380 burns 30 kilos of aviation fuel per nautical mile, which means it could fly roughly 17,000 nautical miles or 31,000 kilometres on the same amount of fuel as a Falcon 9. It's a lot, but it's only 2 and a bit return transatlantic flights, and there's 2,000 transatlantic flights per day in the average year. The last option is Methalox, which is used in SpaceX's Starship. This is based on methane, but when burned it produces CO2, water vapour and a few nitrogen compounds. So it's not as clean as Hydrolox, but it is cleaner than RP1. A single Starship launch using the Super Heavy booster is between 5 to 6 times more polluting than a single shuttle launch, but it can carry 3 to 4 times as much mass to low Earth orbit, so you'd need fewer launches. And without solid rocket boosters, it has a negligible effect on the ozone layer. So here are the numbers that Tim Dodd comes up with. They're slightly uncertain, of course, but correct to well within an order of magnitude. What's the bottom line here? Well, an individual rocket launch is rather polluting, but you also need to bear in mind that there are a few hundred of them per year, whereas there are tens of millions of commercial airline flights. Consequently, emissions from spaceflight today in 2021 are roughly 40,000 times lower than for commercial airline flights. There's also potential to shift all spaceflight to Hydrolox, which is potentially zero carbon if we use green hydrogen in future, or Methalox, which does emit CO2 when burned, but can be manufactured by first extracting CO2 from the air and hence making the total cycle carbon-free. And burning these fuels emits much less water vapour into the upper atmosphere than some of the other competing fuels, and emits almost zero ozone-depleting chemicals. So spaceflight is not clean, but it is a minuscule contributor to climate change, and it will continue to be a minuscule contributor even if the volume of rocket launches increases by 1,000 times. In summary, transport is a challenging area to convert to zero carbon emissions. There are some easy wins, especially for passenger vehicles and smaller buses, but for large ground transport and for shipping, air freight and spaceflight, the conversion is rather difficult. Batteries won't work well because they have a poor energy density per unit weight, and hydrogen is a potential alternative, but currently it's mostly created in an extremely polluting manner. Hydrogen electrolysis and generation of electricity using hydrogen fuel cells may not emit CO2, but it's also very inefficient. The whole cycle wastes roughly 2/3 of the energy coming in. One potential for large shipping applications is to use small nuclear reactors, though the economics there might not work, and there is a considerable public opposition to nuclear fission in general, largely, as I showed in an earlier presentation, based on incorrect assumptions about the nature of nuclear fission reactors and a massive overestimation of the danger they pose. Ultimately, though, road transport currently contributes roughly 3/4 of the emissions across all forms of transport, and it's the easiest to fix, so it should definitely be where we focus our efforts at first. Thanks very much for listening. I hope you continue to listen and join me on this journey through the world of eco-modernism. Next time we'll look at the topic of food and drink. Where does our food and drink come from? And what's the environmental impact? And what can we do about it? This one is definitely going to annoy people, but perhaps not the people you'd expect. So I hope to see you then. For now, thanks for watching.